How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at factors affecting reaction rate. So our objectives will be to explain how various factors can increase or decrease reaction rates. And specifically, we're going to take a look at temperature, pressure, catalysts, concentration, and surface area. So reaction rate is just how quickly or slowly a reaction proceeds. So an example of like a slow reaction might be the rusting of a nail. You leave a nail outside, come back the next day, and it hasn't rusted much. It might take some time to rust. Whereas combustion of gasoline, that's going to be a real rapid reaction. That's going to be really quick. So reaction rate is just describing how quickly these processes occur. So what needs to occur for a reaction to happen? Well, reactants need to collide with each other with the correct orientation and with sufficient energy to break the bonds that are already existing. So here's an example. H2 reacting with Cl2. They have to collide. And in order to get a reaction, the bonds have to break. So you break the bonds that exist. And then new ones can form. And that is literally the chemical reaction. We're changing bondings. So there you go. So anything that will increase this will affect the reaction rate and speed it up. So one thing you might want to consider is state of reactants. For example, increasing the surface area increases the availability for collisions, which increases the rate. So here in the little GIF, you can see trying to ignite this rubbing alcohol is really difficult in the beaker because there's a limited surface area. But when I pour it out, the surface area increases and it burns much more rapidly and readily. So there you go. You can see it. Cool. So why is this? Well, increasing the surface area increases the chances of collisions. So, for example, I have a powdered reactant versus a chunk. So like think a sugar cube versus powdered sugar. Which will dissolve quicker? Well, if it's broken up into smaller pieces, this side would have the higher surface area than the cubed, right? Because if you take a look, this little granule of sugar is in the center, can't even collide with anything, so it's not even available for reaction. And if we take a look, have everything going at the same speed, how many times do those three red dots collide with the cube versus then colliding with any of those spheres, right? So increased surface area means increased reaction rate. Second thing to take a look at, concentrations of reactants. The higher the concentration, the more likely the particles are to collide, so the higher the reaction rate. So solutions, this means if you have a greater concentration, you get a greater reaction rate. And for gases, higher pressure kind of compacts those gas particles closer together, which increases their concentration, which increases the reaction rate, right? So as we increase concentration, the reaction rate is going to increase as well. So why is that? Well, if you have more reactants to collide with, you're going to have more collisions. So you increase their concentrations, or you increase the pressure for gases. And then, here's an analogy. Where would people bump into each other more? A crowded concert or an empty concert? So here, this is the crowded situation. And this one is less so. So we got three people bouncing around in a room. How often are they going to collide with each other? Not nearly as much as here we have 6 dots traveling around, and they're going to collide a lot more often. So here's a chemical example. I have 0.1 molar hydrochloric acid on the left, and I have 6 molar hydrochloric acid on the right. So this is roughly 60 times more concentrated than what's on the left side. So you can see on the left side, we start to get little dots and stuff forming, and you can see reactions occurring. We're making the hydrogen gas. That's pretty obvious. But if you look on the right side, you can see it's happening much more rapidly. This piece of magnesium can't even drop down into the water because there's so many bubbles forming on it. Third thing we're going to take a look at is temperature. So the higher the temperature, the more energy the particles have, and the faster they are moving. This means more of the collisions will have enough energy to react, and there's going to be more collisions. So this is going to increase the reaction rate. So the top example is showing low temperature, and the bottom example is showing high temperature. So you can see with how rapid all of these dots are moving down here, they're going to collide a lot more often than at the lower temperature. So higher temperature, higher reaction rate. Presence of a catalyst. So catalyst changes what kinds of collisions that lead to reaction. They lower the activation energy so that more of the collisions are effective. So if this is my potential energy diagram, I have to invest enough energy to my reactants that it gets over this hump so that it can make products. So what a catalyst does is it lowers that threshold. It lowers the activation energy. So instead of having to go all the way up here, it only has to go up here. So that means it's going to be easier for things to react. So you can see on the right here I have a decomposition of hydrogen peroxide. So this happens naturally at a relatively slow rate, but if we add a catalyst to it, you can see it immediately starts happening a lot quicker, and you can see the bubbles of oxygen forming just from adding the catalyst. Once it's done, the catalyst is still going to be there. It doesn't get used up. So summarize, what is meant by reaction rate? What factors affect reaction rate, and in what way? And yeah, that's it. So I hope you found that helpful. Okay, bye.